There is a fifth dimension, beyond that which is known to man. It is a dimension as vast as space and as timeless as infinity. It is the middle ground between light and shadow, between science and superstition, and it lies between the pit of man's fears and the summit of his knowledge.
I like it raw.
Raw. Ooh, baby, I like it raw.
Ooh, baby, I like it raw.
Science is part of humanity's the very, very first beginning. I mean, we were all sitting around the campfire some 10,000 years ago, looking at the stars, wondering why we are here, where do we come from, and where are we going. As a scientist, the most important sort of character you need is fantasy and curiosity.
Curiosity is why humankind makes progress. Everything that's around you belongs to the result of the curiosity of a person.
I think it's important to keep asking questions because it's a sign of the health of society as a whole.
So CERN is an organization for research, trying to answer the most fundamental questions that humanity ever asked themselves. Where do we come from? I mean, where are we going? What's the future of the universe?
The best brains on the planet sit together. Here, they look for the frontiers of knowledge. They look for the origins of the universe.
For me, one of the appeals of particle physics and high-energy physics in general is that we're really trying to answer the biggest questions in nature. How we came to be, why we're here. And for me, that's really an incredible opportunity.
Pretty much everybody here is driven by trying to find out how the universe works. When you're trying to find out stuff about the universe, the best thing you can do is find a question that you're just barely able to answer within your lifetime.
The way we do particle physics today is in a way by recreating the conditions of the Big Bang. We do that with the help of a collider that we call the LHC, the Large Hadron Collider. It's located in a tunnel which is 27 kilometers long, 100 meters underground.
These experiments that we're trying are really at the edge of what's possible.
A lot of these experiments have been actually working for 20 years, and the questions that we're answering are questions that have been asked for centuries.
If you walk around here, you can almost feel the heartbeat of what's happening here. Something special is happening. We are on the verge of discovery. We don't know what we are going to discover, but the impact of that discovery is unfathomable.
You shouldn't. But you know what I mean? I mean, this sounds so...
You know, it's funny because...
extraordinary when we think about it, because it's the way the world is.
So...
or might be.
Is it really true that what we see is all that's there? Or is it a case where we're just not physiologically designed to experience or see those dimensions, but we'll eventually find evidence of them?
Is there something else out there? I mean, you're a scientist who's exploring these kind of things.
The three spatial dimensions that we know about: left, right, forward, backward, up, down, and time.
I can understand space and I can understand time.
Right.
But I can't understand what might be next. Are we months, years away from understanding the next dimensions?
That's a really great question. It turns out that there will be an accelerator. So an accelerator, particle accelerator, accelerates protons to enormously high energy. And there's going to be a new one that turns on. It turns on in 2007, but really will begin operation in 2008. It's called the Large Hadron Collider, the LHC. It's going to be at an accelerator facility called CERN near Geneva.
The world's largest atom smasher.
Questions of our universe. It's a puzzle that's challenged scientists, scholars, and the religious.
And it was hailed as one of the most significant scientific experiments in history. Well, now the Large Hadron Collider is getting a new piece of kit. Scientists described it as an upgrade comparable from going from a Morris Minor car to a Formula One car.
physicists believe they have finally found the Higgs boson. The initial discovery of the so-called God particle was first announced last July.
The Higgs boson, so far an elusive factor that in theory holds matter together.
The collider near Geneva, Switzerland, crashed 2 proton beams into each other at 3 times more force than ever before.
And we are privileged to witness this event in happening right before our eyes. We are in some sense recreating the process of creation itself.
I mean, does it lead you to believe that, damn it, it's not even, we're just a small part of something very big?
Just a final thought, because you came up with a lovely line talking to our producer saying nature is tricky to understand. Every time you peel back a layer, the universe presents you with something else that you don't understand.
That's absolutely true.
The Large Hadron Collider was designed to replicate conditions seen shortly after the Big Bang. It broke down, though, soon after it was switched on in 2008.
But we'd also learned that nature is a real tease.
The title of your next book, perhaps.
Right, that there seem to be all these hints that we can put it together into a beautiful package and understand things more deeply, maybe learn about the dark matter. I hope that the LHC will take us beyond.
Professor Stephen Hawking say that we might just be around the corner from having a theory of everything. In my experience, that hasn't been the case. Every time we reveal something that we didn't know before, suddenly there are more unanswered questions.
And by the way, the next step beyond the Higgs boson is to find dark matter. We know that most of the universe is actually invisible. It keeps the Milky Way galaxy together, in fact.
So there's quite a lot of evidence for dark matter. If you look at the way galaxies rotate, they don't really fit in a model of the evolution of the universe if there's no dark matter. What's remarkable is you can build a self-consistent model of how the universe has evolved with just one type of dark matter.
Human beings like to be more on the control side, is the possibility of, for example, creating dark matter in the lab.
Then there's the question of why is there more matter than antimatter in the universe? This is really the speciality of the LHCb experiment. At the Big Bang, there should have been equal amounts of matter and antimatter created, and yet there's matter left over, which is good. We're here. It's a good thing, but we don't really understand why.
Now they hope the study will bring new insights into the nature of the cosmos and how it all came into being.
So we don't understand what dark matter is made of. We know it has to be something beyond what we know, and we don't understand why we are here. And we know that there must be something beyond what we know to explain that we are here. Okay, so I think that the LHC will for sure shed some light.
When people say that it's a leap forward from Morris Minor to Formula One car, are they right? Is it of that magnitude?
The technology has come on in leaps and bounds, as one would expect for frontier science.
But one thing that really struck me is how much the search for the Higgs boson captured the public's imagination to a significant extent, really. I mean, there was journalists from all over the world kind of queuing up to report on it. Why?
This gets to your question of whether this is a special time in history. I think it's a very special time in history. It's as if we're fish who've suddenly discovered that they live in water.
Why do you think that was the case? I don't remember a scientific event that caught the public's imagination to that level for a very long time.
Jerome Friedman, your former colleague at MIT, I think said that if we see evidence of what has been proposed by you. It will be extraordinary. It will shake up everything. It's pretty good.
That would be pretty good. I mean, it's true. I mean, it could be that we need to get to a little bit higher energy to learn more, but right now we think we will definitely learn something at the energies that we will explore. But there could be even more exotic phenomena, like higher dimensional.
It's a really incremental step.
It's not incremental in the sense that it's 7 times the energy of current accelerators, so it really is the right energy to probe these questions. It's just that if you get a little bit more energy, you might learn a little more. For example, if you get to even higher energies, you might be able to make higher dimensional black holes if this idea is right. So there are new things that could occur with higher energy. But we do expect to be able to know the answers to these questions from the Large Hadron Collider. I just want to clarify.
What's likely to be another dimension?
What do you mean by that?
Well, I mean, there are 4 dimensions.
Yes.
What would be a 5th? What would be a 6th?
Art makes life worth living. Because via art, I think we can discover beauty, whereas science makes us live free, because only with science and applying logic and requiring proof, we can be free from swallowing any rubbish propaganda. So I work at CERN so many years, I never noticed all these things are so beautiful. But I just want to show you some of the pictures here so that you can see how we at CERN took some photos, and you look at them and you are ému, you are sort of moved, because they contain worlds within the simple photographed item. You can see things that are there from reflection in the grass. You can see a ladder that goes to heaven. There is such a majority of devotion to the projects that it's sort of sublimination de l'environnement. So you can see several of them where you have the impression that it's like the end of the world as we know it.
LINAC 2 dates back to the 1970s, so the technology that's been used for LINAC 4 is considerably more advanced. It allows you to control those proton beams much more precisely, and also gives you control over much greater quantities of protons, which is what you need for investigating the experiments that they have on the Large Hadron Collider.
Where we're exploring the mysteries of matter. Now, the LHC is a particle accelerator. It's the largest, highest energy particle accelerator in the world.
We're talking about a machine that'll take us right to the beginning of time itself.
There will be people who try to piece out from it what were the different, they'll test the different ideas. So lots of people have suggested what might be there. But generally they're going to look for energetic particles, they're going to see where did they come from, what could have been, what was producing whatever they found.
Because when you're talking about a technology like this, or about geoengineering, this is something where even beginning to do the work in the laboratory means you are making a decision that could affect people outside the laboratory. And if you do that work behind closed doors, and make no mistake, virtually all of science is kept secret from everybody until the moment of publication, because the incentive system is set up such that if you tell somebody else your genius idea, some other lab is going to go off and do it, rush it, publish first, they get all the credit, you get none. This is an insane way to set up your scientific system. No one in their right mind, building it from scratch, would say we should do it this way. And yet we do, because that's the way we have always done it. It never worked great, even before the cost of sharing information went to zero. But if you want to engage with a community, how can you do that if you're only telling them what the technology is when you've already gotten it working? Then it's too late. Then you're going to the FDA for regulatory approval. You get the public comment period. But no matter what people say, you can't do anything. It's too late. Done. Finished product.
The synchrocyclotron emerges,
piece by piece. Some 54 elements are put together for the magnet frame. A total of 2,500 tons of steel. Next, the two 7.2 meter diameter magnet coils are installed. With a current of 1,800 amps, they generate a magnetic field of 2 Tesla. The rectangular vacuum chamber is fixed inside the magnet. A system of large vacuum pumps is installed to evacuate the 25 cubic meter chamber so that protons can circulate unimpeded. This is followed by the installation of 2 D-shaped electrodes inside the vacuum chamber. Together with these electrodes, a radio frequency generator creates the electric fields. That accelerate protons from a source inserted in the center of the vacuum chamber. In summer 1957, the synchrocyclotron is ready. And CERN's first accelerator comes to life. The purpose of the synchrocyclotron is to produce and study new particles. Before accelerators were available, such particles could only be observed in cosmic ray experiments. The new machine accelerates protons to 80% the speed of light, producing millions of new particles when those protons collide with the target, giving scientists the opportunity to make systematic measurements. Operation of the SC requires a sequence of actions. Massive pumps extract the air from the vacuum chamber so that protons do not collide with gas molecules during their acceleration. In the proton source, hydrogen gas is ionized and a cloud of protons is injected into the middle of the synchrocyclotron. The accelerator makes use of magnetic and electric fields. The magnetic field is produced by a current of 1,800 amps flowing through the coils of the huge magnet. 2 D-shaped electrodes with opposite polarity are fixed inside the vacuum chamber in the middle of the magnet. Protons have a positive charge and are drawn towards the negative electrode as they traverse the gap between the electrodes. The magnetic field forces them to follow a circular trajectory, and they return to the gap after 1/2 turn. Meanwhile, the radio frequency generator reverses the polarity between the 2 electrodes. The protons are now attracted to the opposite electrode and gain more energy. This process is repeated over and over again. Every time the protons make a 1/2 turn, they are whipped around faster and the radius of their path increases. After more than 100,000 turns, they have reached an energy of 600 million electron volts and move at 80% of the speed of light. They are now close to hitting the target, and the first experiment can begin.